Welcome to the webinar 2 of the webinar series, Data Science, Machine Learning, and AI Applications and Opportunities. Today's webinar is focused on manufacturing analytics or use of data science and machine learning in manufacturing domain. So I want to briefly introduce the topic and our panelists before we basically move on to the panelist presentation. Manufacturing in general could be defined as the fabrication or assembly of components into the finished product. It is one of the most important industries in the world's economy, and it is estimated that nearly 16% of the global GDP is focused on manufacturing. And it has generated an output of nearly $13.9 trillion globally. And one of the main critical aspects of manufacturing is to produce or manufacture high quality products at a minimum cost. As of the last decades, we have seen a paradigm shift in the manufacturing industry where the manufacturing industry has entered what is termed as Industry 4.0 or Fourth Industrial Revolution or smart manufacturing. And it is given rise to an emerging sector in manufacturing that opens the door for analytics or use of data science and machine learning. Essentially, it's a technology-driven approach that utilizes IoT, Internet connected data, any form of data to produce or monitor processes. And the main goal is to automate the processes involved in manufacturing to maximize efficiency, to increase sustainability, and to enable supply chain management, along with identifying some system barriers that can occur even before they occur. Now, with the application of advanced analytics to industrial data, manufacturing can gain insights to optimize the productivity of individual assets as well as total manufacturing operations. And the key impetus here in this paradigm is basically the use of machine learning, data science, and artificial intelligence. And this webinar is actually focused on that topic, or the manufacturing topic. So once again, welcome to the webinar. And what I want to do is, before I introduce the panelist for today's talk, I want to take a quick few minutes to talk about the next webinar panelist, right? So we have in next week webinar 3, which will be occurring on 15th July 21. That also is focused on manufacturing and manufacturing applications of data science. And we have Thomas Herdward from Applied Research Lab at UMD, Lynn Myers from Clemson University, and Dr. James Kong from Virginia Tech giving talk on the manufacturing analytics. So if you're interested in this webinar, the next webinar also is going to be very, very relevant to you. So with that, let me introduce the panelists of today's webinar. So we have 3 main panelists who are participating. First, we have Dr. Thorsten Wuest. Dr. Thorsten Wuest serves as an associate professor at West Virginia University in the Benjamin Stetler College of Engineering and Mineral Resources. His research is focused on smart manufacturing, machine learning, data analytics, AI/ML, and hybrid analytics, Industry 4.0, and product service systems, as well as item-level product lifecycle management with focus on smart manufacturing system. In his research, he puts an emphasis on an interdisciplinary and holistic approach toward analysis and optimization. He is recognized as a smart manufacturing thought leader and is listed among the top most influential professors in smart manufacturing by SME, which is Society for Manufacturing Engineers. In addition to publishing his work in premier outlet in his field, he has been also featured in Forbes, Futurism, Industry Week, World Economic Forum, CBC Radio, and World Manufacturing Forum too. He is involved in several professional societies, and among them, he is Vice Chair Americas for IFIP Working Group and is a member of IFI WG 5.1. He is also a member of Provost's Academic Transformation Committee and serves on the West Virginia Faculty Senate and has also served on many strategic teams at West Virginia and in his college. With that, let's welcome Thorsten and let's move on to The second panelist of today's talk, which is Dr. Ying Liu, who is currently a reader in intelligent manufacturing and the group leader for high-value manufacturing with the Department of Mechanical Engineering at the School of Engineering in Cardiff University, UK. Before that, he worked as an assistant professor with the Department of Mechanical Engineering at National University of Singapore from 2010 to 2013, and with the Department of Industrial Systems and Engineering at Hong Kong Polytechnic University from 2006 to 2010. He obtained his bachelor's and master's both from Mechanical Engineering at Chongqing University, China, and PhD from the Innovation and Manufacturing Systems and Technology IMST program under Singapore MIT Alliance at National University of Singapore. His research interests primarily focused on engineering informatics, digital and intelligent smart manufacturing, AI and machine learning from engineering, design, and process advancement. He has published more than 160 scholarly articles and edited several books, and have been a specialist guest editor for more than 15 journals that he has done. His career trajectory was supported by GRF Hong Kong, MOE Singapore, A-Star, and many other different companies. Currently, he serves as an associate editor for ASME JSI, IEEE ASC, and multiple different other journals. With that, let's move on to the third panelist of this webinar, which is Satish Bukkapatnam. Satish serves as a Rockwell International Professor with the W.M. Michael Barnes Industrial and Systems Engineering Department at Texas A&M University, and is the director of Texas A&M Engineering Experimentation TEES Institute for Manufacturing System. He is a fellow of IISC and SME and has received Oklahoma State University Regents Distinguished Research and Fulbright Tocqueville Distinct Chair Award. He received his PhD and MS degree in Industrial and Manufacturing Engineering from Penn State. The Society of Manufacturing Engineers SMS magazine listed him among the top 20 most influential professors in smart manufacturing, the inaugural class. His research has yielded more than 115 journal publications and 73 conference proceedings, 1 patent, and has received over 7 million in grants and contracts as PI and co-PI with the government and private sector. So with that, I welcome all the panelists, and we'll start with Thor or Thorsten as the first speaker for this panel.
All right, thank you so much, Rahul, for this opportunity and the invitation. Let me share my screen. I've prepared a few intro slides to introduce our work and the topic. And before I start, just a quick orientation how the slides should be perceived. My understanding is that this webinar series is not exclusively for manufacturing. So that's why I tried at the beginning to frame that a little bit and put into context why analytics is so important for manufacturing in our opinion, I believe. That being said, let me just give a quick shout out to our team, because most of the work in academia is done by our teams. It's not done by yourself. So a shout out to our Smart Manufacturing Lab here at WVU with our talented students that work on all these projects that we will introduce here. And second, shameless self-promotion, our recent book. If you're interested in data analytics, just starting off on it, I highly recommend it. It's available on Amazon, obviously, but it's a good introduction in the whole data analytics space from a supply networks perspective, including manufacturing. All right. So when we now talk about data analytics, machine learning, I think it's very important to put the process into context, and it all starts with data, right? So we have to acquire data, and in manufacturing, a lot of the data is acquired from our machine tools, from our shop floor processes, from sensors, from other systems like MES or scheduling processing software. The data that comes out of that is not ready to be analyzed yet. Pre-processing is key. We have data quality issues. We have different formats, different provisions that we have to put together. We have to see how the distribution of the data is, if that aligns with our statistical analysis, and so on and so forth. Then we have a bunch of different machine learning models, algorithms available nowadays, very conveniently in Python or in other software that we can apply to our problem. And then we have to make sure that this algorithm aligns with the software. We have to train our model, right, to make sure that it can do the prediction that we intend. Once we have our the first iteration of our model created, we have to evaluate, does it really do what we want it to do, right? Then we can tune the parameters of our model, of our algorithm to improve even more, given the particular problem space that we're operating in. And then we can apply it. We can put it in a container and put it into our business process to do what it's intended to do, right? That all is an iterative process. Like, you don't just do that once and you're done. Data updates, the process changes. Every problem is different, so we might go through that multiple times. Most of you probably know that. This is not new to you. One thing that I always emphasize is a lot of people seem to focus directly on model selection, model training, and put a lot of time and effort on that, or just focus too much about that. But in manufacturing, I believe the data pre-processing is actually much more important, because there the data understanding is crucial. The quality that you understand, what data you put together, what you can actually derive as an insight from the data that you acquire, will inform what the model can do later. And as a rule of thumb, talking to industry, but also from our own experience, 80% of the time should probably be spent on understanding the data, cleaning the data, working with the data before you then apply your model selection and so on, which nowadays can almost be automated, right? There's the automatic model selection processes that can be applied. The second higher level thing that I would like to address here real quickly is in manufacturing. Manufacturing is so broad. Raul already scoped the space from, producing a single individual screw to a whole car, a system that you assemble, right? This is a big difference in what problems you want to apply data analytics for. And on the part level, I just put a semiconductor here because that is a well-developed area of data analytics and manufacturing. We have a pretty good understanding of what we want to achieve, how the physics behind it will work out, and how data analytics can be applied here. The higher we go, like in the machine tool space, we normally have control over it. It's not trivial, but it is possible to get the data out of a machine tool in most cases, and it's a process where you can work with the machine tool, understand the data quality, understand what you have, what you don't have. But the higher you go up in that space, all the way up to the industry level, the problems become much more organizational and less technical. So the data analysis might not be as model dependent or as granular, but more political. Who is willing to share your data, what you can do with the data, who can profit from the insights. That is a very important aspect, I believe, that we will see more in the near future. All right, and when we talk about data, there's a bunch of different issues that we face in manufacturing, not exclusively, but definitely something to work with. Unbalanced data sets. When we talk about production data, we have not many bad examples. And for a good reason, because a company that would produce 50% scrap material would not be in business very long, right? 50% scrap material would be great to train most models, because they would like to have a good balance of good and bad examples when you apply that as a model criteria. But there are ways to go around that, and this is very important to develop that space more in manufacturing. Data quality issues. Obviously, the sensors are of different granularity, but also the transfer of data, the timing of data, and missing data values. How do you handle those? Can be very tricky in a manufacturing setting. Another trivial point, but important point is you can only analyze what is measured, right? When you don't measure a certain instance or don't include it in your analytics, well, you might not understand that that is a driving parameter, a driving factor of your decision process, and your model might just not be as accurate as it could be if you include that point as well. There's also something that, called too much data, that the feature space being too big, and the example space too little. So a lot of interesting problems. That being said, I will jump over that because I'm talking already too long. A few projects that we worked on recently where these issues that I just mentioned played a role in. This is a project that I know very well because it was part of my PhD. So I worked on that myself very detailed. And what we had here was we looked at multi-stage processes, right? Like manufacturing is not just one process and done. Normally you have a succession of different processes, different technologies. And to this point, still, it's very difficult to integrate that into a data set, because a lot of times you source from one company to the other, and the data is not part of the deal. You get the part, but not the data of the process before it. In this case, what we did, we applied support vector machines to try identify the driving features of a multi-stage process. And one of the use cases in the aerospace industry, we got an anonymized data set, and with the model that we applied, we ranked the features and gave it back to the experts to see if that actually made sense, because we just got parameter 1, 2, 3, 4, 5, not the detailed description. And they came back and said, parameter 1, 2, yes, we know they are very important. Parameter 3, I don't think that's important. We don't even know why we included that data point in the data set, right? Okay, well, that's not the result that we wanted, right? But 2 weeks later, they called back and said, like, hey, we looked into it, and it actually has a big impact. Even so, it's not one of the core processes that we're normally looking into. It was something like a fan, like an auxiliary process that was not directly changing anything in the physics of the part. But overall, it showed that it has a big impact on the part quality, which I found extremely fascinating and supporting the point you can only analyze what you measure, right? So sometimes it makes sense to include something where your gut tells you, oh, that won't make a difference. Well, you don't know. All right, just checking the time. I think I'm still good. The next project is with a company that has a lot of legacy systems in the field. And what they experienced was for their after-sales services, they often had to fly through, or the whole of the US. And coming from Europe, the US is really big. So they had to travel like 8-9 hours just to realize, oh, the failure code on the HMI on our PLC output told us we need to replace part XYZ. And the company didn't tell them. So they traveled there, saw that failure code, basically had to go back, order the part, and drive over there or fly over there a few days later again when they had the part. So their initial idea was, we want to connect our legacy systems to the internet, to read out PLC error codes to optimize our after-sale services, right? Working with them, we realized, hey, when you connect your legacy systems to the internet and go through that trouble, why not, monitor them through an online interface that you can put on a tablet, that you can put on any computer where you want. So we worked with a startup and that company to develop that system. And my intention from the start was, okay, once we have that data, well, then we can also work with that data and develop insights and basically cluster all the events ideally, and maybe even do some predictive maintenance, predictive analytics on the data set. 1 year in, when we had our test applications installed, we got a data set for a year and ran in all the trouble that I described before. The data was not clean, right? Big data set, but not very clean, a lot of missing data. And whole hours missing. We had no access to the experts on the shop floor that actually operated the machine. So we saw on the left bottom side, you see some of the clusters we were able to identify, but we don't know what they mean in the context, because we only know, okay, this means the heat of the dryer hopper might drop in a certain fashion. But that can have a multitude of reasons. It can be intentional. You can just shut down the machine, right, on the weekend. It could mean there's a leak. It could mean you have a supply problem. Without context, it's very hard to model and to cluster these events. Nevertheless, what we then did, we used different projects to first of all identify the windows of the different events from steady state to different event types without putting a label on it, because that we need the expert for. And right now, one of my students, who I think is in the audience, is working on his master thesis to identify and cluster one of the events using a deep learning or neural network. Moving forward, we hope that we can do that for a multitude of these different clusters to help the company to flag certain events. We saw in the data that one of the machines was running through a long weekend, the 4th of July weekend, I believe, without being supplied material, but at full heat. What a waste of energy, right? And having the right labels will allow at least to alarm and see, like, is that intentional? Do you really want to blow warm air through this the whole weekend without any effect? Most likely they won't, but this is just one of the lower level applications. And then the next step would be, can we predict what will happen? And that is always tricky in such a process, because a lot of it is triggered by the operator, and some might be intentional, some might not be. And it's not like a bearing where you see a gradual decline or so. It might be just somebody presses a button or somebody shuts off the supply at another system that then has an effect here. But advanced warning would be important, because you have a 2-hour window. When your hopper goes under a certain level, you have 2 hours. After that, you have to shut down your injection molding machine or you produce scrap parts. And every company wants to avoid that, obviously. This project, I think Raul will recognize that, and Shub as well, because that's a collaborative project with Raul's group and West Virginia and a company in Etamco, where we propose to work on a grinding process of large end gears. And use a hybrid approach, basically combine physics-based modeling and machine learning to optimize the energy efficiency of that process. These are 1 meter diameter gears that use like 11 hours to be produced, and they use a lot of energy. And in the process, there's different steps: grinding, but then you have to dress and repurpose the wheel, which also takes a lot of energy. And right now, that is not optimized based on how it's used, and that is what we want to address utilizing both physics modeling and data-driven modeling. The last project is kind of like a pet project that we started out of an opportunity with working with a colleague in Youngstown State, now El Paso, Eric McDonald. We have that system in my lab where we have a heating tunnel. And we thought, hey, a lot of the products we use nowadays are smart products. They have sensors, but these sensors are not utilized in the beginning of life. They're only utilized in the usage phase, right? So we thought, can we utilize that in the system itself? So the idea was, you have a sensor in a product. Well, can the product basically tell you what happened to itself instead of having the sensors in the machine tool? And so we captured a bunch of data and then used, again, a neural network to cluster these different events, like the heating event, the turning event, and the flipping event. They're very unique and pretty easy to cluster. All right, I know I went a little bit over, I believe. That's why I stop here and hand it over, I believe, to Ying, or back to Raul first.
Yes, the next speaker is Dr. Liu. I think you're muted, Dr. Liu.
Yeah, that's right. Many thanks, Rahul, for inviting me. It's my great pleasure join you guys today, share with you my research. And this is entirely, as Thorsten also mentioned, that this is entirely done with my former PhD students. My topic is called Embracing Manufacturing Informatics for Smart Manufacturing. So in the UK, we have a different organization defining manufacturing informatics as different concepts. So the first one is talking about manufacturing informatics is a research relating to the use of new and emerging ICT tools and the information methodologies for future manufacturing technologies, process, and the system. So this was from EPRC, which is one of the national funding agency primarily for engineering and the physical science. And we also have another version from EMRC at Sheffield. This is the Advanced Manufacturing Research Center, Catapult. So this is like an equivalent version, sort of like a Fraunhofer Research Institute in Germany. So by EMRC, they define manufacturing informatics as a part of their wider EMRC digital manufacturing thread. So encompassing the IoT, all right, and the big data and the data-driven manufacturing technology. So this was coined in 2014. And then myself, for some people who know me well, so I basically come with a version of a manufacturing informatics as studies the representation, perception, processing, computation, communication, storage, retrieval, and the reuse of information and the knowledge in the context of a manufacturing environment. So I was giving this topic first in 2007, when I went to Loughborough University and the University of Bath in the UK to give a talk. At that moment, I was actually working in Hong Kong. So if you're looking at my definition, you will see some terms that people usually do not really bring up. For example, representation. How you represent data and the information is quite critical. It's a part of the pre-processing, especially nowadays, we are dealing with lots of multimedia data, so not just numerical data, yeah? And also perception, interact with humans. And if you look at also storage, retrieval, and reuse, so you will think probably I have background with PDM, PRM. And when I was working at my PhD, so I actually work a lot on information retrieval plus natural language processing. So that's why I bring all this together, and I believe that is what manufacturing informatics is supposed to do. It's quite comprehensive in some words. So particularly look at the scope of the topic, of the concept. It includes different dimensions. So the first one I wish to mention is from the ICT perspective. For the time being, people like to call this as a digitization or a digital foundation of the application domain, for example. And from manufacturing background, we know a lot of things like PDM, PRM, distributed or networked manufacturing, and so on and so forth. So another major branch is what we call cognitive and the social science. So I have been talking about this for the last probably 15 years for some of the colleagues who know me well, but it's only until very recently I started to actively working on these branches, because in Cardiff University, we happen to have a bunch of colleagues who are so well, fantastic. They have a fantastic research on cognitive science, on psychology. So we talk to each other, and quickly we found lots of, interesting topics we wish to work out together. For example, we try to bring machine learning help with their experimental psychology, and we explore what this could do or means for future, digitized next generation smart factories. Yeah, so it's my ambition for the next, 5 years. Yeah, I wish to invest probably 4 or 5 PhD students along these branches. And of course, we have different manufacturing systems, from automatic assembly to the FMS or computer integrated manufacturing, for examples, and all the way to nowadays we talk about Industry 4.0 and beyond. And then lastly but not least, we also have computer science and artificial intelligence, AI and machine learning. In the past, some people call, if you are coming from a knowledge database background, you call knowledge discovery in database, human computer machine interactions, personalization, visualization, and so on. So it's really at the cross-cutting, it is this center. That's what I call manufacturing informatics. So most of my PhD students, they need to work with this kind of multidisciplinary work. And I strongly believe I was blessed, because half of my PhD students, they come from engineering, say manufacturing, mechanical, industrial engineering background, but half of my PhD students in the past, they come from computer science background. So it's very difficult, actually, if some of you may know, it's very difficult, to attract computer science students coming to engineering to work on some of these topics. So that's why I said I was, extremely blessed. So in the next, I wish to share with you some examples that I have been working on, joining with my PhD students. The first one is probably very hot topic because recently we are working on a review paper on machine learning and its research and application in additive manufacturing. This is primarily on how to apply machine learning data analytics, for example, into additive manufacturing or 3D printing. And we primarily looking at energy consumption. So when we work on this, we have two primary motivations. The first one is we wish to help designers at the early stage, for example, when they're working on the design, to gain some ideas, with their design, with their features, with their preliminary material selections, how much energy would that going to cost? And this is because at the moment, if you're talking about AM technologies, there are so many different types of AM technology processes, and also there are so many builders, OEM manufacturers for the machines. So we don't really know well the process, how it's going to, what's going to happen, and how the energy is going to be consumed. So in that case, if we wish to advise, design engineers in the beginning or in the early stages to have some ideas that in what way you do design, in what way incorporate, different design features, for example, and in what way you actually jointly produce different number of part components together, that you could arrive at a relatively lower consumption in terms of power consumption, right? But also we are looking into the future, right? When one day AM as a technology will be joining the shop floor as other conventional manufacturing technology really ready for mass production. Yeah, we strongly believe that day is coming very soon. So when that happens, energy consumption moving towards net zero, for example, is definitely something very critical we need to investigate. So this is very much the motivation why we want to engage in this part of our work. Another work project we want to share with you is concerning about multifaceted, conceptual modeling while information fusion. So the particular example I wish to surface is we're working with steel making industry. We look at some materials, right? Silicon steel going through the cold rolling process so that we want to make the material, thinner and thinner. So when we trying to analyze, the process, we usually encounter a failure or critical status, which is called strip breakage. So the material during the cold rolling process, they just break up. And this is notorious. And this is actually quite, chaos caused problem. So in the past, engineers had attempted to address this issue from different dimensions, from mathematical modeling, looking from applied physics perspective, looking at the mechanical property. Some engineers work in the factory for 20, 30 years. They know this process very well. They know under what combination with process parameters, material, and what would be, say, for example, specifically being what kind of a lubricant, including coolant, you are going to use, which will arrive at a more steady process. But they cannot express that in an analytical model. So that's the limitation of some empirical knowledge. But also some, engineers has attempted to install smart sensors along the process. They catch a lot of data, but they don't know how to explore such data. So what we are doing here is trying to promote a multifaceted sort of a conceptual modeling by using information fusion and looking at the fused outcome in terms of what would be the probability for the breakage to happen. So we really synthesize almost all rounded information, and we found out that this has been very effective. And the third one I wish to share with you is something we call process mining. We started this work a little bit early in 2008 at that moment. So basically what it tries to do is when you have a collection of some footprints, say, including your emails, for examples, but primarily are the data logs, right? So we go through the processing, process mining process, different algorithms. So eventually we want to extract, an underlying process model that has been, deployed to support the process. or to support the project. For example, we use event graph to represent the underlying process. And then once that has been uncovered, we could carry out any sort of a discrete event simulation so that we could actually steadily deploy. But the key point here is not about the process or process mining. It's about what would be the fancy outcome from this process. So in this case, what we're trying to do is we create a problem space, a 3D problem space structured by one dimension like personnel, yeah, and the one dimension based on the time sequence, and another dimension based on the task you are going to do. So this fancy 3D space, in each dimension, you can already do a lot. For example, if you're looking at the personnel, you can almost apply everything about social nets. Looking at the project team, you know, what's happening when the project was executed. But if you look at any of these two dimensions, for example, between personnel and the task, you would be able, if you drill down, you would be able to identify something we call resource planning. Resource is not just about the equipment or whatever, or monetary things, but it could also means knowledge capacity, right? So if you're looking at what happened in the past project, you will have good ideas why some engineers work together quite nicely. And when they have a very hot discussions representing some very peak performance, but why for some topics, they become relatively quiet. So that could be likely because there's a missing of knowledge. So with this 3D space, we could do a lot. So I'm very happy to discover in the last about 2 or 3 years, a lot of efforts has been globally, what I have been aware of, that has been, you know, invested in something like this. So let's see what's going to happen in the next probably 5 years. And the last topic I would wish to share with you, we are not the only one working on that, is on predictive maintenance, one of the mainstream topic. We use data mining, we particularly use deep learning to help, you know, company to do that. And we have been donated with 3 million of fleet, you know, maintenance data. So probably this is the largest amount, the highest amount of the data resource we have acquired from our industry collaborator. So what we did is we actually suggested some kind of a unified generical info analytical model for the maintenance, for predictive maintenance. We look at the vehicle as a whole piece level, but we also could drill down looking at component level. So if the technology could penetrate into the maintenance, for example, if smart sensor can be deployed, if communication with no problem, including 5G, or even sometimes satellite communication. So you would be able to collect such data, even at the part and component level from the vehicles. So with that, we could actually drive down and do a lot of deep work. We link this research with garages for inventory management. So in that sense, we could easily justify, you know, return on investment, some of these business KPIs. So this is what we did. So lastly, but not the least, because we are in higher education, right? So, you know, besides we work on cutting edge research, actively collaborate with our industry partners, we also focus on education. So this is one of the postgraduate module I initiated, you know, in Cardiff in the academic year 2014 and 15. So I call this as a manufacturing informatics. So for the prescribed counter hours, I spent 1/3 teaching students about, say, some fundamental concepts about machine learning or data mining. And the 1/3 of the time, we let the student to learn a machine learning or data mining tool. And the 1/3 of the time, I categorize that for students to work on some industry, you know, that kind of a great projects. So in this case, for example, I show you this one is from steel making industry. We take the energy consumption data from, you know, electrical arc furnace. So we understand that we are putting lots of, you know, steel scraps in the furnace. We, for one go, one operation, they spend it because of the configuration of the scraps are different. So every time we will go for operation, that is the furnace will spend different, will consume different energy. So we take records, thousands of them, we give to students and ask them to model and predict. So what I'm trying to see here is, besides, you know, teaching students or equip our students with this best concept about machine learning and the data mining, but what more important is we equip students with the essential knowledge and the skill on problem formulation. Yeah, so we are standing really at application domain like manufacturing, but also trying to bring AI and machine learning into application. So we are really standing at the interface between two domains, and through our module, hopefully our students will be able to understand how they can take advantage of such source for some realistic manufacturing problems. And with such knowledge and skills, our graduates are highly demanded in industry. Yeah, I have to report this, it's highly demanded. Some of them got a contract, a job even before they graduate. Yeah, that's some very exciting news. So for the time constraint, I would reach to finish here and then return the floor to Rahul. Thank you.
Thank you, Dr. Liu. And then we'll move on to our next speaker, Satish.
Yeah. Are we able to see my screen?
Yeah, it is coming up, Satish.
Excellent. Again, good morning, good afternoon, and good evening to all of you. Again, nice to connect with all of us to talk about this very interesting emerging topic. Intentionally, I kind of titled it AI, as opposed to just focusing on machine learning alone, AI for smart manufacturing and Industry 4.0. And again, there is a selfish reason to do that, because my research as well as the things that I do fall right into this area of smart manufacturing. Specifically, if you want to define what I do, I look at precision aspects of manufacturing, a variety of processes in different industry sectors, and looking at sensors and measurement aspects in those processes, as well as applications and some development of AI theory and principles for these applications. And what I hope to do in the next 10 minutes or so is to give a glimpse of what I do with my group. And again, nothing is possible without my students, Afreen, Bhaskar, Asif, Akash, and Zemo. All that I'm presenting today is based on what they have done and what they're doing. And I also represent Texas A&M's TEES Institute for Manufacturing Systems. And I would like to kind of begin by telling where I am from and what we do. Our group is one of the largest manufacturing groups in the nation. We now have over 40 faculty members, and we specialize essentially in 4 aspects. And one of them happens to be smart manufacturing, which I'm associated with. And we also have some world-class facilities developed, especially in the last 5 years. And we have launched several national as well as international initiatives. Especially, we have a very thriving program called Transatlantic Partnership with France and other European nations. And also we have significant engagements happening in Qatar and India. And in the education front, we have developed significant manufacturing focused programs at all levels of engineering, starting from bachelor's and all the way to PhD specializations. And we probably will be a thriving program for those of us interested in pursuing advanced learning in manufacturing, specifically in the area of smart manufacturing. And when it comes to smart manufacturing, let me begin by providing my spiel of how I think about smart manufacturing. To me, smart manufacturing is basically a composite of the recent advancements and revolutions that have taken place in different facets of technologies, be it communications. The previous speaker talked about 5G and beyond, and advanced sensors, especially imaging sensors, material systems, computing, cloud, and other kinds of architectures, clean energy, and last and not the least, AI and data science. How they all come together to advance manufacturing processes, not just additive, not just semiconductor, all forms of manufacturing processes where you can transform materials into valuable products. And our research group actually has been looking at different aspects of smart manufacturing. And one of the important facets of smart manufacturing is it is something that a lot of industrial conglomerates are embracing. And more important than everything else, it is extremely vital for small and medium companies, as well as startups, to start thinking about how they will become part of the smart manufacturing ecosystem that's going to come up. And one of the challenges that will be presented in this context is data. And that's where AI comes. Manufacturing, as noted by one of my recent graduates, Asif, actually produces the largest amount of data compared to any other manufacturing sectors or any other industry sectors. And be it government, transportation, and so on, the manufacturing produces large amount of data. However, very little of the data that gets generated actually gets used in the industry. And the use of data science, machine learning, the things that you may be interested in, would be extremely important to really make full use of this data. And through the remainder of 5 minutes or so, I will give some glimpses as to how they can be useful and what kind of impact you will have from looking at these AI types of methods. But when we look at AI, please remember that first thing that comes to our mind is machine learning. We think about neural networks, deep learning, and so on. But there is a lot more to this beyond this machine learning. Machine learning in general focuses on prediction. And beyond prediction, essentially given X, you're trying to come up with a Y. And what you're seeing here is one of the deep learning architectures that we had to put together to address a problem in sustainable manufacturing area. Beyond that, we have representation theory. Essentially, how do you take a scene and then represent it in a way that can be useful for decision making? So here you're taking an image of an SCM, and you come up with a graph representation of it so that you can use it for monitoring purposes. Similarly, you have a stream of data, and you can come up with a representation that will help us detect changes in the process. And beyond representation is discovery, forecasting, prognosis, diagnosis, control, and so on. Everything kind of comes into the big picture of building AI suite for manufacturing. And also another thing that I wish to share here is it's not just sufficient to take the out of the box methods and apply it to manufacturing and hope that it will work well. So there has to be a sustained and focused effort in machine learning and AI, particularly for smart manufacturing. And I will try to kind of talk about the ways in which the manufacturing focused AI and ML can be a little bit unique. First of all, just because you have data and you have toolboxes available, you don't have a solution. You somehow need to have good understanding of the manufacturing context and then try to come up with what is the best way to address the manufacturing problem, and then see if any of the existing techniques would be helpful. And given the scenarios that we dealt with, including the problems that were nicely laid out by the previous speakers, the first issue is the data will be streaming, especially if you want to make real-time decisions. You have to somehow harness data where you're collecting data at the rate of few gigahertz every second, right? And also you have multidimensional data, and then you have to synchronize them. You have to look at the timeliness issues. Second is, if you look at manufacturing data, you can have streams of data, very little ground truth available. So the data oftentimes, or vast majority of the data is unlabeled. So you have to resort to techniques beyond supervised learning. In other words, deep learning will not work here, okay? And of course, there are some variants that people have been looking at and so on. We can talk about that. And also other thing is, you don't have one type of data. If you look at a manufacturing context, it's not just a point source. As Thor nicely laid out, it's actually a multi-step and highly distributed. How do you use this data for making useful predictions? And how do you fuse physics or the process information to improve the learning? These are some exciting challenges that are unique to manufacturing, where people with strong interest and capabilities in machine learning and AI can really thrive. And also, let me spend a little time talking about the things that we do here. To set the context, as I mentioned earlier, the vast majority of the machine tool platforms or manufacturing platforms are with the small and medium enterprises. And what they have are processes for consolidation. It could be a casting process, a additive manufacturing process, machining, heat treatment, grinding, polishing. Everybody has their own niche, and they have some of these combinations of these processes. And especially if you want to create a service-oriented paradigm for manufacturing, these processes need to be integrated together. At Texas A&M, we are working on a platform called Smart Hybrid Manufacturing. It's a machine tool that integrates these processes. And more importantly, these processes are completely monitored using heterogeneous sensors. For example, we can monitor the process in real time using video images, forces, acoustic, vibration, and so on, so that through the images, you can observe, if you observe any kind of a defect, you can go back and look at the process and tell what was happening to the signal at the time when you saw this defect, and go back and look at the product and tell what was happening to other aspects of the process. For example, are you looking at some patterns of the forces, vibrations, and so on, while at this point you saw this defect? Or you're observing some other anomalies in the process like spatter. So essentially, you can actually have a multi-dimensional inferencing system developed by synchronizing this data. And there have been studies that talked about how much you can increase case by case the throughput, and how much you can reduce defects and cost and so on. So there are lots of fantastic advantages that come from fusing this information cleverly. And also you can optimize this process, coming up with optimal thermodynamic pathways, and also deal with the issues of cybersecurity. And another thing that we could possibly do with this type of capabilities, essentially by fusing manufacturing focused AI, is to look at the issue of in situ monitoring of defects. Defects especially become extremely troublesome and pesky when it comes to newer processes. As the industry tries to insert a new process or a new variant of a process, they have to deal with this problem of assuring quality and qualifying the whole process again. And sensor technology has developed, but the data that comes from these sensor signals are not oftentimes labeled. So we need to come up with a supervised learning method. In one of our recent works, again, Professor Asif Iqbal, who's now at Arizona State, he developed a very elegant graph-based methods with which you can very, very quickly segment out the portions that are likely to contain defects. And it's not just about honing on the defect portions, but you can track them as the process evolves as to what's happening to this defect. So you can come up with a label-free approach to learn the defects in a process and monitor them. The other facet to this whole exercise here is the information fusion. The manufacturing enterprise is filled with various different data sources. And if it's anything, it's actually growing at a very rapid pace. For example, the manufacturing execution systems, they are growing at about 20% annual rate. And the IoT sensors are growing at 40% every year. And they are like a 300 billion market. And they generate significant, basically petabytes of data every hour. And they're multimodal, as you can see. IoT sensor data will have a different format and different kind and so on, right? But if you can somehow harness this information, people have said that there can be significant savings and significant improvement in the productivity and energy efficiency. At the same time, these data can help us avoid some major catastrophe, especially if you think about smart manufacturing systems that are highly connected. A fault at a particular point or a breakdown of a machine at any one location will have a serious ramification throughout the enterprise. So if we can cleverly harness this information and maybe predict big breakdowns well in advance, as opposed to just detecting them after the fact, it can actually have a radically different kind of capabilities for fixing as well as rewiring the manufacturing system, so to speak. And in one of our earlier projects, we addressed the same thing. Without going into the details, Details can be gathered from some of the publications that I'm going to lay out at the end of this conversation. We can go at the beginning of any shift of a manufacturing line. And the typical assembly line can have 20 different machines. We go there and apply analytics, use the historic data of when various machines actually failed, and we can actually predict to a fairly good extent, even the machines that are going to fail in the next half an hour, and reasonably well at the throughout the entire shift. So we walk into a shift, look at the historic data, and look at what machines are vulnerable to fail without having any kind of real-time monitoring capability. That is the power of analytics that we have now. Not just that, it's not just about prediction, but also inference, explanation, and possible discovery. That is where I think machine learning can make a big impact in manufacturing. So a person in the shop floor will not only get an information that some machine is vulnerable, but also can give an information about why a particular machine can be vulnerable and what can be done to effectively fix them in future. And combining this historic information with real-time IoT can be significantly more powerful. And this is one of the challenges that we are currently working on. And given the interest of time, let me conclude by saying that manufacturing presents some very unique and very interesting and I believe fascinating challenges for those of us engaged in AI/ML. And three areas where I think significant differences and uniqueness emerge is in the streaming nature of high dimensional data, the challenges with images, lack of labeling, and the heterogeneity and need to fuse in both space, time, as well as context. And with that, I would like to hand it over to Rahul. And if anyone's interested, feel free to ask me questions or follow up on the contents, because most of what I presented have already been published in my prior works. Thank you, Rahul.
Thank you very much, Satish. We have still some time for a couple of more questions. So one of the questions that, since our audience is mainly student, is what sort of skill set is required for a person to come into data science and specifically into manufacturing analytics domain? So if somebody has done an undergraduate and willing to pursue a master's degree in manufacturing analytics, what sort of skill set they should have, or what sort of skill set is good for that kind of degree?
Rahul, let me begin. I have had, been blessed to have a lot of wonderful students, and most of my students come with a degree in what I call as core engineering subjects: mechanical engineering, production engineering, and industrial engineering. They already come with a good understanding of manufacturing processes and the underlying physics. And some of my best students were able to pick up data science as well as anybody else. And their pursuits were that much enriched because of their deep understanding of the manufacturing. So in other words, it's not difficult for someone from the core engineering subjects to become an expert in data science. And and also those of us who are from computer science and data aspects, they can be very good at the systems aspects of manufacturing. And I probably would would like to hear from other colleagues here.
From my perspective, I also wish to share with our students, besides skill sets, you probably wish to think about what kind of a mindset you wish to bring forward if you join, data science or any of these relevant MS modules. I wish to stress curiosity first, and the hands-on spirit, especially if one day you need to deal with programming. So curiosity means that you need to see how, if you apply some of this knowledge and the skills into a domain application, because eventually you are going to do this, if not manufacturing, maybe healthcare, maybe in the financial market, it may be for hotel and tourism management. So you are going to encounter this, because for data science to take off, to really make sense, it's when it gels with an application domain. Yeah, so that is the moment really why you see the returns. Yeah, you feel excited, you feel the achievement. So with curiosity, that will prepare you, thrust you, help you to drive yourself, to find anything interesting, looking for sense making, significant questions, and blah blah. And when you spot that, you quickly action on that and start doing that with hands-on. Don't wait, doing a little bit, because compared to 20 years ago, like Thorsten also mentioned, we spend so much time in pre-processing data. But nowadays, many tools and application platforms in the cloud, for example, they have already automated the data pre-processing, at least to a very large extent. So help you to, for example, dealing with missing data, dealing with errors, for examples, which is much simpler than, say, 20 years ago when I started dealing with some manufacturing data. It was so dirty in that sense, right? So prepare yourself with this, spot some more digitally, curiosity-driven, hands-on, quickly apply doing this, and see what you can do, whether that's insightful, exciting, you discovered. I would encourage that spirit as a part of the mindset. Yeah. Going to colleagues.
Yeah, just to add briefly, I agree with both of you, and I think what Satish mentioned especially is having an understanding of manufacturing processes and the acceptance that it's based in the physical world, and that the output should be explainable at some point is very good. And then the curiosity, saying like, okay, I will try it, and when the results are surprising, I will go back and find out why they didn't work, or if they are like they are, why is it surprising? Why didn't we know about that? I think this manufacturing driven domain expertise is a great foundation to go into data science here. Other way around, it's a little bit more difficult because manufacturing is a particular area that you need some background to interpret the data and understand if your prediction makes sense or not.
Thank you. I think we have time for one more question, and I will take this question asked in the question and answer. Is like, and this is for all the panelists. How will manufacturing analytics change job roles in manufacturing, and how will it affect the evolution of undergraduate curriculum here? So how do you see that evolving in over a decade or a couple of decades from now?
Well, I guess we go the other way around. So
That's what I mean.
keep it very short. Well, I think there is actually a World Manufacturing Forum report from 2019 looked at the skills for the future of manufacturing. And a lot of them stress that curiosity, that problem solving, and that openness to learn. And I think that would be not directly related to data science, but being open to change how you do your job today. And that applies also to the curriculum. Like maybe we need to add some flexibility in our approach to undergrad education there in capstone project, where we just give them a part problem of our research, or allow them to explore a new way of analyzing data using Python, or go adding a competition on Kaggle, just to allow them to explore and to be open-minded in that space. I think that curiosity, I like the word curiosity, is crucial. And how we can implement that within ABET and all the rules that we have to follow, that is a challenge for all of us on the other side of academia, I guess.
Right. So from my perspective, I could talk about this for hours. So to keep it short, I often talk to my PhD students. I have a series called left hand and the right hand. It's very simple. Let me explain. So the left hand basically is, because we are in engineering, including some of you actually in computer science. So we basically applied the series or laws from physics, applied physics, for example, to tackle some engineering problem. And this is very true for mechanical and the manufacturing. So I call this, left hand. But at the moment, we are facing lots of data coming. So this data represents empirical, observations, for example. When it is small, you probably don't bother for that. But when it comes at a certain quantity, thousands and more, you probably wish to leverage it from all these empirical observations, right? And think about what can you do with that? Leverage them, become case study, become principles. Maybe one day they could emerge, as a theory. And in that case, you apply the theory that you uncovered, right? bike into the knowledge pool, and then you use the left hand to apply. So left hand and the right hand, you should use them simultaneously and harmonically. Now, in the past, at least based on my undergraduate education experience, right hand has been left less focused. So I did study mathematical modeling, but it was not like now we are actually using AI or the machine learning or advanced data sciences, right, to really deep penetrate into the data and leverage that, right? This is what we needed. So I would say for sometime in the near future, such modules or education will become the core part of undergraduate education, which I'm aware of in some countries. This movement has already started. So hopefully the message is left hand and the right hand for science, especially natural science and engineering, we should use both of them harmonically. That's my key message. Thank you.
Yeah, I mean, this is nicely put, both Thor and Ying. Essentially, the future curriculum has to deal with both atoms and electrons. In other words, you have to deal with the science of the atoms, as in material science, process physics, mechanics. At the same time, we need to deal with the science of electrons and energy, right? So dealing with the information, dealing with the issues of as Ying mentioned, right? He's dealing with the social scientists, still looking at these kinds of things. So it is going to be a great interdisciplinary endeavor. And going back to the question that Rahul asked, what is it that you can expect for, what is it that you want your students to learn? Yes, it has to be a deeper science of the process, because without knowing the context, the solutions can be just suggestions, right? We want to know the process. At the same time, we need to have the acumen to apply some of the latest technologies, especially the AI/ML that is going to evolve very rapidly in the next few years, to be able to put them to use to these contexts. So it is a balance. Right hand, left hand is a good thing, or right brain, left brain is a good thing. However you think, it has to be an interdisciplinary but harmonized interdisciplinary approach that needs to be taken. And I believe the ABET and other types of regimes will be up to the task right now, because it's going to be a challenging, at the same time, an exciting time.
So I would like to thank all the panelists for taking their valuable time and spending that time with all the participants that we have. I really appreciate your participation. And with that, I will also just conclude by saying that next webinar, which is webinar 3, is also going to be focused on manufacturing analytics, and I look forward to your participation. There are still some questions that we have not answered, and I will personally reach back to some of you with the answers to those questions. With that, thank you everyone for participation, and I will look forward to seeing some of you in the next webinar too. Bye.
Thank you, everyone. Keep in touch.
Bye. See you.